There is a rare moment in astronomy when two sequences of observations tell the same story, yet seem to describe two completely different objects. Imagine tracking an interstellar visitor crossing the solar system, observing its behavior for weeks, recording every detail with telescopes and probes. And then, almost without warning, it radically changes its appearance in a matter of hours. Not because it became something else, not because something mysterious intervened, but because it finally entered the most critical phase of its entire journey: the direct encounter with the sun's heat. That is exactly what happened with 3I Atlas. For weeks, it appeared to be a relatively calm, predictable, and even discreet comet by cosmic standards. A silent visitor following a hyperbolic trajectory, quietly slipping through the solar system without drawing much attention. Early data showed a thin coma, a stable tail, and brightness increasing gradually, exactly as the models predicted. Everything fit the textbook description of how a distant comet should behave as it slowly approached the inner solar system. Nothing out of the ordinary, nothing that suggested we were about to witness a rapid and dramatic transformation. But then, a curious detail emerged. There was a gap in public observations precisely when the object was approaching the most important point of its orbit, perihelion, the moment when a comet receives the greatest amount of solar energy. This is the phase when deep, ancient ice begins to react, when pressure builds beneath the surface, and when the outer layers of the nucleus can transform in a matter of hours. It is the moment when a comet reveals what it is truly made of. And it was exactly during this observational gap that a Chinese orbital probe around Mars managed to capture something extraordinary. From its unique vantage point, far from Earth's line of sight, the spacecraft recorded new images that completely changed the narrative surrounding 3I Atlas. The data revealed an object far more active, far brighter, and far more dynamic than any previous record had suggested. The transformation was so striking that, at first glance, it seemed like an entirely different celestial body. But it wasn't. It was the same interstellar visitor, simply in a new stage of its interaction with the Sun. The encounter occurred on October 3rd, when 3I Atlas passed closest to Mars. This alignment created a brief but invaluable window of observation, allowing scientists to study the comet from a fresh geometric perspective. And within that short interval, something changed rapidly. The coma, the vast cloud of gas and dust surrounding a comet's nucleus, expanded dramatically, reaching about 250,000 miles in diameter, roughly 3 times the size of Earth. Such a rapid expansion is not just a visual change, it is a physical signal that intense sublimation had begun. Ice buried deep inside the nucleus was suddenly turning directly into gas, escaping violently into space and dragging enormous quantities of dust along with it. Beyond simply growing larger, the coma developed sharper edges and an unusual brightness facing the Sun. This detail is crucial. A sunward brightening suggests that fresh material had recently been exposed, volatile compounds that had never interacted with solar radiation before. In other words, layers that had remained frozen and untouched for millions or even billions of years were suddenly being uncovered and released into space. This kind of sudden activation tells a deeper story about the comet's structure. It suggests fractures opening beneath the surface, pockets of volatile gases rupturing, and jets of material erupting like cosmic geysers. These processes can reshape a comet in a matter of hours, altering its brightness, its shape, and even the direction and structure of its tail. What makes this moment especially fascinating is that it captured a transition in real time. We are not simply seeing a comet before and after perihelion. We are witnessing the instant when solar energy begins to dominate the physics of the object, the tipping point where a quiet interstellar traveler becomes an active, evolving comet under the Sun's influence. The tail also revealed clear signs of this transformation. In the last images previously released by NASA, it appeared straight and pointed away from the Sun, exactly as expected from the basic physics of comet tails. But the new images showed a slight curvature toward the Sun, something that suggests the opening of new jets of material on the surface. This type of change happens when parts of the nucleus begin releasing gas and dust from regions different from those active before. In other words, the surface began to wake up. Another detail drew even more attention. The internal distribution of dust changed. The brightness pattern indicated the presence of larger grains, which means deeper layers were exposed to solar heat. Before, the data pointed to a thinner and more homogeneous cloud. Now, there were clear signs of heavier material being ejected. This suggests the heating reached regions that had remained protected for millions, or even billions, of years. Spectroscopic analyses reinforced this change even further. New measurements pointed to a much stronger signature of carbon dioxide than previously detected. This type of ice usually remains buried in deeper layers because it is more volatile. When it begins to escape, it means the heating has reached regions that were previously isolated from solar radiation. It is like opening a frozen time capsule preserved since the object's formation. These changes happened rapidly, within an interval that does not appear in NASA's public data, and this created a curious gap. Before perihelion, the comet looked stable. During perihelion, it appeared extremely active. The simplest explanation is that each dataset captured different moments of the same event. Perihelion, the point in the orbit when the comet passes closest to the Sun, is precisely the most important phase for observation. This is when solar heat vaporizes the ice and reveals the internal structure of the nucleus. During this period, the object's behavior can change in a matter of hours. NASA described the absence of observations as a routine pause for instrument calibration, something common in large observatories. The problem was the timing. Maintenance coincided exactly with the most valuable moment of the passage. Without continuous observations during this interval, scientists lost the chance to track in real time how the object reacted to peak heating. That is where the Chinese images filled the gap. They showed the moment when the surface began reacting to the Sun in an intense and rapid way, something that normally only happens when deep layers begin to fracture. When the two datasets are aligned chronologically, the story makes sense. NASA recorded the calm phase before perihelion. China recorded the moment of activation. Together, they form a complete timeline of the object's transformation. The first major change appears in the coma. In older images, it was thin and faded gently. In the new ones, it became wide, bright, and well-defined. This indicates that large amounts of gas and dust were released during the unobserved interval. Heat can penetrate through fractures or pores in the ice, reaching deep pockets. When these pockets rupture, the release can be sudden and explosive. The change in the tail reinforces this interpretation. The curvature toward the Sun suggests the opening of a new jet at a different angle. Even a small jet can alter the shape of the tail because the released dust travels vast distances quickly. On a cosmic scale, a small change in direction can produce a massive visible alteration. The increase in brightness was also striking. While earlier measurements showed a gradual rise, new observations indicated an abrupt jump over a short interval. This type of increase is typical when deep ice fractures all at once. A famous example is Comet 17P Holmes, which increased its brightness hundreds of thousands of times within a few days. The 3I Atlas event was smaller, but followed the same physical pattern. The composition of the dust provided another important clue. Before, fine particles from the surface layer dominated. Afterward, larger grains appeared mixed throughout the coma. This suggests deeper, more compacted material was exposed. This evidence indicates that the nucleus contains internal layers preserved for a very long time, like intact pages of an extremely ancient book. The new measurements also helped refine the object's trajectory. During the active phase, gas release generates small forces that can slightly alter the nucleus's path. The additional data reduced orbital uncertainty by about 30%, showing that the activity was real and measurable, not merely a visual effect. None of this indicates a conflict between the datasets. They describe the same object at different moments of its interaction with the Sun. The difference lies in the timing of the observations, and that detail completely changes the scientific interpretation. With only the initial data, the object would appear calm and predictable. With the full sequence, it becomes a classic case of rapid activation near perihelion. This changes how scientists plan to observe future interstellar visitors. These objects do not return in closed orbits. They enter the solar system once and then disappear forever. Every minute of observation is precious. Losing critical hours can mean losing part of the story. The stronger carbon dioxide signal suggests the object formed in an extremely cold environment rich in volatile ice. The heavier dust indicates a long history of slow compaction. The burst of activity shows that these layers can remain stable for millions of years and still react violently when heated. This event also highlights the importance of continuous observational coverage. Rare objects require intense monitoring during perihelion, when they reveal their deepest characteristics. Now, 3I Atlas is moving away from the sun and beginning to cool. The coma should slowly shrink, the tail will become thinner, and activity will decline. Observatories around the world plan to follow this final phase to understand the speed of dissipation and the chemical evolution of the ejected material. Over time, all these observations will be combined into a single timeline. The calm approach recorded before perihelion, the burst of activity captured during peak heating, and the gradual dissipation that follows. This complete sequence shows how an object from another stellar system reacts to a star different from the one where it formed. In the end, the new images do not point to alien technology or any extraordinary phenomenon beyond the physics of comets. They simply reveal the moment when the object shifted from a calm state to an active one. And that moment was exactly the missing link needed to understand why 3I Atlas appeared so different in each record. This interstellar visitor is not just a comet. It is a sample from another stellar system, carrying clues about the chemistry and formation of worlds beyond our own. And the perihelion observations revealed that these building blocks are more dynamic and reactive than we imagined. If you made it this far, take a moment to like the video, subscribe to the channel, and comment on what you think we can still discover about interstellar visitors like 3I Atlas. Because the truth is, we are only beginning to understand these messengers from afar, and every new observation can completely change our view of the universe.